So in this section, we're going to be looking at static rigid bodies. The clue's in the name. These are going to be rigid bodies that are not moving. Most commonly, these are going to be questions about ladders. So we'll look at a few cases. The first one is a ladder resting against a wall. So just making sure we get the sketch correct. There's a reaction force perpendicular to the ground. And if it's a rough ground, there'll be a frictional force as well. There's a reaction force perpendicular to the wall. And depending whether or not the wall is smooth or rough, there may need to be an additional friction force as well. Okay. Secondly, we have questions that involve pegs. So a peg is something that sticks out from the wall that can hold something in place. So I'll just represent this as a circle. And here's the ladder or plank resting on that peg. What forces do we have? We have a reaction force perpendicular to the rigid body. We have reaction force perpendicular to the ground. And we have a frictional force parallel to the ground, since this was rough ground. All right, and the last one, maybe the trickiest, is a hinge. If we're told that a static rigid body is hinged, this is the diagram that I'll use. It's usually held in place by a string or a rope. So there'll be tension in that rope. There will be forces in two directions. So these perpendicular forces operating at the hinge. Sometimes you may be asked to talk about the direction and magnitude of the reaction at the hinge. And we will just need to treat these two forces like vectors and use that to respond to the question. Okay, so those are the three main cases that we will come across. Be on the lookout for each of them. They basically start with the exact diagram that I have here for you, with careful attention to whether or not there is friction on the wall or on the peg, etc. So is it a smooth or rough wall, smooth or rough peg? Okay, let's get into a couple of examples. Okay, so in this example, we can see that we're working with a ladder that's resting against a wall. So first I'll just sketch the wall and the ground. I was told that it was rough horizontal ground and it was a smooth vertical wall. So we're told a load of mass 2m is fixed on the ladder at point C. So here I'll indicate C, and that's 2m for the mass, so 2mg for the weight. The distance from A to C is A, so I can label that on. Remembering this is a uniform rod, I can show the mass of the rod should be at 3/2a. That'll be halfway of the 3a. So to make sure that to get from A to the midpoint is 3/2, I need an additional half A, and the rest of the rod is 3/2a as well. I was told it inclines at 60 degrees. So most of what's given to me in the question I've represented. Let's not forget to add the forces. So the perpendicular reaction force and a frictional force at point A, and a reaction force at point B. Since I'm working with a triangle, I might as well just represent each of these angles. Okay, so we're also told it's in limiting equilibrium, so we know that the maximum friction has been activated. So let's go ahead and resolve. As usual, we'll use the three techniques that we are familiar with. So resolving horizontally, resolving vertically, and taking moments. So for this particular question, I'll start by resolving vertically. All of the upwards forces should equal all of the downwards forces. So R1 should equal 3mg. Resolving horizontally. All of the horizontal forces to the right should equal all the horizontal forces to the left. Mu R1 equals R2. All right, be careful. If there were any non-parallel or perpendicular forces, we would have to break them down into components and use them as we resolve in these two directions. Okay, so next, let's take some moments around point B. So think of all the forces we need to involve. There's mg, 2mg, R1, and mu R1. Each of those we're going to need to consider what would be the moment from B. A reminder, to calculate the moment, we need the perpendicular distance from the point we're taking moments from to the line of action. So to the force line, or an extended version of the force line. So I just need to be really careful for each of these cases. What exactly will it look like? So I'm going to sketch each of the individual cases just to show how we're generating those moments. So for the mg, here's my line of action. And here's the portion of the original sketch that I'm using. So just from B to the midpoint, just from B to the line of action mg. So I've extended that line of action above the static rigid body. All right, so a length of 3/2a and the angle 60. The dotted line is the perpendicular distance I need for the moment. For the force 2mg, a similar thing. That was going to be 2a in distance, so for the hypotenuse, and I've shown the force and the angle. Okay, so both of these are going to be anti-clockwise forces. One more anti-clockwise force, and it's going to be the mu r. Okay, so AB, there's the force mu r. Here's the perpendicular distance from the line of action to the point that we're taking moments from, and that I would need to calculate. Okay, these are all the clockwise forces, the anti-clockwise force. These are all the anti-clockwise forces. The clockwise force is going to be R1. So in a similar way, I want to indicate the perpendicular distance we're looking for. That's the dashed line. The length AB, as it has been throughout the whole question, is 3a. All right, so I've just got a visual representation of each of the moments that I'm going to try and calculate. This will help to keep it clear in my head exactly which calculations I should be constructing, and it allows me to come back and check through my work afterwards. All right, so mg is the force. The perpendicular distance is the hypotenuse multiplied by cosine of the angle. 2mg is the force, hypotenuse multiplied by cosine of the angle. So magnitude of the force multiplied by the hypotenuse, and this time it will be sine of the angle, so sine 60 this time round. Okay, and altogether that should equal the clockwise force, which will be R1 multiplied by the hypotenuse times cosine 60. Okay, so from here we can just go ahead and simplify. A is a common factor, so I'll just take that out. I'll just write everything a little bit neater, expanding the brackets. and really looking for opportunities to make this whole expression, this whole equation, easier to work with. All right, let's not forget that we had already found a value for R1. R1 was 3 mg. So actually all of these have mg in common as well. So there's a common factor of mg, which we can go ahead and eliminate. So at this point, I'm actually happy to rearrange to make mu the subject. So I'll just have some fractions to deal with. 3 over 2, 4, and the 9. So 9 minus the other 2. And then I'm going to divide that by 9 sine 60. Okay, at this point is actually the first point that I'm going to reach for my calculator. Plug this into the calculator, and we get mu equals, and from there we get 7 root 3 over 54. Okay, so in this question, a uniform rod AB has mass 40 kilograms and length 10 meters, and it rests with one end on horizontal ground, and the rod rests against a smooth peg C. All right, so we'll just start with a diagram for a peg. Here's the peg. We have rough ground here, so we'll go ahead and add some forces, perpendicular reaction force and friction, and a perpendicular reaction force at the peg as well. Okay, it's a smooth peg, so there's no friction on the peg. If we were told it was a rough peg, we would indeed need to add the friction there. Okay, so let's label up some more. We know there's an incline of 15 degrees. It's a uniform rod with a mass of 40 kilograms. So its weight is 40 G. I can add these lengths. Once again, it's uniform. So that weight operates at the center of the rod, which was 10 meters. And the peg was indeed 8 meters away from C. Okay, reaction and friction and my second reaction force. The first part of the question asked me to calculate the reaction at C. All right, so I've got all of my techniques available, resolving horizontally, vertically, and taking moments. I'm going to choose moments because I know if I take moments from the point A, let's label that A, that will eliminate the unknown values at A. They don't need to be considered to calculate moments. So the only unknown I'll be working with is the unknown of R2, the reaction force that we're looking for. Okay, so I'll go ahead and start by taking moments. Okay, since the 40G isn't perpendicular or parallel to the rod, I'm going to quickly draw a diagram to help me calculate the moment correctly. The perpendicular distance to the line of action of the force is going to be 5 cosine 15. Okay, so that was the point of the diagram, just to quickly make sure I've got the right value. Anyway, that's the only clockwise moment, and the anti-clockwise moment, a lot easier to find. It's 8. That's the perpendicular distance to R2. 8R2. All right, so just some quick rearranging, some smart rearranging. Now I'm ready to pick up the calculator. And this is the first time I will. Plug it in, and we get a reaction force at C of 237 to 3 significant figures. Okay, we've also been asked to find the coefficient of friction between the rod and the ground. We'll go ahead and do that. Okay, so from here, I will go ahead and resolve horizontally first. And just being extremely careful that R2 does have a horizontal component that I'm going to need to consider. So I'll draw a mini diagram just to be clear about those components. It may not fit on my larger diagram. Okay, what would the angle be? Well, we know it's perpendicular to the beam, and an alternate angle at that point would be 15, so the angle inside must be 75. Okay, so resolving horizontally, mu R1 must equal R2 cosine 75. Okay, so I've got an expression for mu R1, and of course we have a value for R2, so just calculating that to be 61.3. The three significant figures. Okay, let's go ahead and resolve vertically this time. We've already got a quick diagram, so we know the vertical component of R2. So R1 plus R2 sine 75 should equal 40G. All right, and I just really need to rearrange to get an expression or a value for R1. And then mu R1 and R1, I can use them to find out exactly what mu should be. Okay, so 40G minus R2 sine 45. This can go into the calculator, and 163 to three significant figures. Okay, mu is going to equal 1 divided by the other. 61.3 divided by 163. Okay, so it's going to be quite a small coefficient of friction. Into the calculator, and we get 0.38.